Have you ever heard a developer say, "But it works on my machine"? I'm sure you have. Well, that one single, incredibly frustrating phrase is pretty much the key to understanding a technology that has completely changed the software world: containerization. So if you've ever wondered what containers are all about and why everyone seems to be talking about them, you are in exactly the right place. We're going to break down the fundamentals nice and simple.
Okay, so to really get why containers are such a big deal, we have to talk about a problem. A classic, hair-pulling, keyboard-smashing kind of problem that has plagued developers and IT teams for, well, decades.
And there it is, the infamous line, "It works on my machine." So, picture this. A developer spends weeks, maybe months, building a new feature. It runs perfectly on their laptop. It's smooth, it's fast, it's beautiful. They hand it over to the testing team, and it just breaks. It completely falls over. And why? Because the environments are different. Maybe the developer has version 10.1 of a certain library, but the test server is running version 9.8. That tiny little difference can cause a massive, massive headache. And that exact headache is the entire reason containerization was born.
So, how do you solve a problem like that? How can you possibly guarantee that an application's environment is always going to be exactly the same every single time? Well, the answer is a really elegant solution called a container. It's a simple idea, but it's an incredibly powerful one that promises consistency no matter where your code is running.
At its absolute core, containerization is all about packaging. You can think of it like this. It's a technology that lets you bundle up an application with everything it could possibly need to run, all its code, all its settings, all its dependencies, and you wrap it all up in a neat, lightweight, isolated little box. The best analogy really is a standardized shipping container. It doesn't matter what's inside, the box can be moved and stacked and run anywhere.
So what exactly are we putting inside this box? The short answer is everything. I mean, literally everything the app needs to live. You've got the application code itself, of course, all the libraries and other pieces of software it depends on, the specific runtime it was built for, like a particular version of Python or Node.js, and of course, any configuration files. It is a complete, totally self-sufficient package.
Now, right about now, you might be thinking, hold on a second, isn't this just a virtual machine? And that is a great question, probably the most common one, and the difference is absolutely crucial. A virtual machine, or a VM, has to run a full, separate, entire operating system right on top of your main OS. This makes them really heavy and kind of slow to start up. Containers, on the other hand, do something much smarter. They all share the host operating system's kernel. And because of that, they are incredibly lightweight. They can start in seconds, and you can cram way more of them onto a single server.
Okay, so containers are lightweight, and they're consistent. That's cool, but why did this one idea become such a massive, industry-shaking game changer? Let's take a look at the really big wins. The benefits here are just huge. First and foremost, consistency. This is what solves that works on my machine problem once and for all. We've talked about how they're lightweight and fast. They also provide fantastic isolation, meaning a crash in one container won't bring down its neighbors. They're unbelievably scalable. Need more capacity? Just spin up a few more containers in seconds. And of course, portability. You can build a container on your laptop and run that exact same container on a server in the cloud without changing a single thing. It just works.
So we know what containers are and why they're so powerful. Now let's pop the hood a little bit and see how this whole thing actually works. It's actually not that complicated. We can break it down into a simple 4-layer stack.
Okay, so let's start at the bottom. The foundation of everything is your host operating system, think Linux, and its core component, the kernel. Sitting on top of that, you have the container engine. The most famous one is Docker, and its job is to be the manager, the one that builds and runs all the containers. The engine uses a template, which we call an image, to create the final piece of the puzzle, the container itself, which is your live running application.
Let's just zoom in on that image layer for a second. The absolute best way to think of a container image is as a blueprint, or maybe a recipe. It's a static, read-only file that has all the instructions and all the ingredients needed to create a running container. You make this blueprint one time, and then you can use it to build as many identical copies as you want. And that, of course, brings us to the container itself. If the image is the blueprint, the container is the actual house built from those plans. It's the live, running, interactive version of the application. And the real beauty of this system is you can launch hundreds, or even thousands, of perfectly identical containers all from that one single image. And this brings us back to what is really the secret sauce, the reason why containers are so incredibly efficient. Unlike VMs, where every single one needs its own bulky operating system,
All the containers running on a machine share the host OS kernel. This just saves a gigantic amount of memory and CPU power, and it makes everything so much faster and lighter.
But that does raise a really important question, right? If all these different containers are sharing the same brain, the same operating system kernel, how do they stay separate? What stops them from messing with each other's files or processes?
Well, this is where a couple of really clever features built into the Linux kernel itself come into play. The first one is called namespaces. Namespaces essentially give each container its own private, isolated view of the system. It's like putting blinders on each container so it can only see its own stuff, its own processes, its own network, its own files. The second tool is called cgroups, or control groups, and their job is simple. They put a leash on each container, limiting exactly how much CPU and memory it's allowed to use. This prevents any one container from getting greedy and hogging all the resources.
All right, so we've dug into the what and the how. Now let's zoom back out and connect the dots to see how containers really fit into the bigger world of modern software development.
You see, containers are the foundation for a lot of really powerful modern ideas. Take immutability. This means that instead of trying to fix a broken container, you just throw it away and launch a fresh, perfect new one from the image. It makes your whole system so much more predictable. We've already talked about scaling, and for the world of DevOps and CI/CD, this whole build once, run anywhere philosophy is a total game changer for building fast, automated pipelines.
But of course, there's a catch. What happens when you're not just running a few containers on your laptop, but you're running hundreds or even thousands of them, spread across a whole fleet of servers? Well, trying to manage all that by hand is, well, it's just impossible. You need a new tool, a whole new layer of automation to conduct that chaos.
And that tool is called an orchestrator. Think of it like the conductor of an orchestra. Orchestration platforms, and the undisputed king of them is Kubernetes, are designed specifically to manage containerized applications at massive scale. They take care of everything automatically, deploying your containers, scaling them up or down, handling all the complex networking, and even healing them if they crash.
So we really come full circle, haven't we? We started with a simple, frustrating problem, and we ended with a solution, containerization, that has fundamentally solved portability and consistency in software. We can now build an application one time and have total confidence that it will run exactly the same way anywhere. So the big question to leave you with is this. Now that that massive problem is solved, what's next? What new incredible things can we build now that this foundation is in place?